Good morning. Welcome to Lionheart Academy. This is Richard Tai. Today we're continuing our trigonometry lesson. Today is lesson number 35. We have been talking about inverse trig functions for the past two lessons. Today is our third lesson. We'll be looking at some application and problems. How do we use trig functions? One of the way we use trig functions, or one way to understand trig functions a little bit more, is to understand the composition of functions. Now we have done a little bit examples of that before, so let's go and try that. So one of the ways we can do composition of functions would be to put the arctangent. Okay, so for example, what would be arctangent? For example, we're going to mix everything up of sine of 3 pi over 2. Alright, so in this kind of problems, what we do, we have to evaluate the inside first. We have to find out what's the sine of 3 pi over 2. So using our unit circle, or if you can remember, 3 pi over 2 is 270 degrees. So sine of 3 pi over 2 will be down there, will be -1. Alright, actually no, I'm sorry, sine of this 3 pi over 2, yeah, is -1 because it's down. Sine follows the y order pair, so if you imagine it going down, it's -1. And arctangent of -1, it should give us an angle in quadrant 4. Okay, an angle in quadrant 4. So let's just go ahead and make sure everyone remembered the quadrant definition there for arctangent and arcsine, arccosine, and all that. So we're gonna have our arcsine. If we even put a positive value for arcsine, it will return an angle between 0 and pi over 2. Okay, and arccosine does the same thing. In fact, all six of them are up here when they are positive. Okay, but arctangent is going to give us, when we input a negative value, arctangent will return an angle between 0 and pi over 2, so it will be fourth quadrant. However, even though it's in fourth quadrant, but it's going to be from 0 to pi over 2 rather than from 3 pi over 2 to 2 pi. We're not going to use those sections in our arctangent. And arccosine is here. Arccotangent is here, okay, from pi over 2 to pi, and from pi over 2 to pi, we will have arcsecant, and then arccosecant. Okay, all right. So when we see arctangent of -1, we ask ourselves which quadrant should we go to? We should go to the fourth quadrant from 0 to pi over 2, and so that angle that fits that criteria is pi over 4, because our regular tangent of pi over 4 is equal to 1, and so pi over 4 is down here. Arctangent of pi over 4 will be equal to -1. Okay, all right. So let's go and try another example here. So cosine of arccosine of pi. Okay, so let's go and take a look at the inside first. So what is arccosine of pi? Well, arccosine of pi represents an angle. It represents an angle that allows us to say, okay, which angle has a cosine value of pi? Well, if you look at this, which angle has a cosine value of pi? Well, we could use we could have used this to help us out. We could have used a calculator to help us out. But if we look at this, what is the domain for arccosine? Remember the domain for arccosine? If we remember, the domain for arccosine has to be between -1 and 1, because the output for cosine is between -1 and 1. So when we do arccosine of pi, pi is outside the domain range. You see, when we do arccosine of x, x has to be between -1 and 1. Alright, so in this case, pi is greater than 1, right? Pi is 3.1, about 3.14159, and so on. So pi is greater than 1. So in this case, this is undefined. Why is undefined? Because pi is outside the domain of our cosine. So this is undefined. So we cannot take cosine of an undefined function, undefined value. So the expression is undefined. Okay. So we got to make sure that we stay inside the range. We got to stay inside the range. All right. Let's try another one. How about let's do tangent of arctan of -5. Now the input of of arctangent is from -infinity to positive infinity. So the x for input is all the way from -infinity to positive infinity. Okay, so we can put in anything like that. And arctangent, so -5 is definitely within the input. Okay, therefore the tangent of arctangent of -5 just return us -5, because now the inverse functions, they will cancel each other out. Okay, they will cancel each other out. Let's try another one. What about arcsine of sine of 5 pi over 3? Okay, so as we talked about this before, we need to go ahead and answer the inside first. Okay, we need to find out what sine of 5 pi over 3 first. Alright, so let's remember our unit circle. 5 pi over 3 is in fourth quadrant. Yeah, 5 pi over 3 is in fourth quadrant. Okay, so sine of 5 pi over 3 is negative square root of 3 over 2, negative 3 square root of 3 over 2. And when we have arcsine of negative square root of 2, it will return us a negative angle in quadrant 4. Okay, so which angle in quadrant 4 has this value? Well, it's negative pi over 3. Now you notice that 5 pi over 3 and negative pi over 3, they are actually coterminal angles, but they are not the same angles. So it returned a negative pi over 3 rather than 5 pi over 3, because the angle, even though 5 pi over 3 is still in fourth quadrant, but the measurement of arcsine is only returning angles from 0 to negative pi over 2. That's why those are the angles that's being returned. Okay, so we have down some opposition function. As you can see, if we have cosine of arcsine, it will return as long as our input is within the domain, and we will be able to get exactly what it back. I think I would like to go ahead and summarize that for a little bit. Okay, but if we do arcsine of a sine function, then it might not work, because it really depends on what exactly input we have. Okay, so for example, let me go ahead and give you a rule here. So if we do sine of arcsine of x, will we get back x? Well, we will get back x if x is between -1 and +1. That means if x is between is in the actual domain. Okay, if x is actually in the domain. Now, but however, if we do arcsine of sine of x, well, will we get back to x? Well, only if x is between negative pi over 2 and pi over 2. So this is, again, is the restrictions on our inverse composite functions. So there's a restriction in the output, in the input, in what we will get back. So if this x is not within pi over 2 and negative pi over 2, then we will not get the x back. Okay, so same thing for cosine of arccosine. It will be equal to x if x is between -1 and 1. And what about arccosine of cosine? Arccosine of cosine x will be equal to x if x is between 0 and pi. Okay, but otherwise it will not be the same. Now, what about for tangent? Alright, let's write it down. So tangent of arctangent of x will be equal to x if x is any real numbers, basically, in this case. Now, what about arctangent of tangent x? Okay, arctangent of tangent x, okay, will only be equal to x if x is between negative pi over 2 less than x less than pi over 2. So in this case, x cannot be equal to pi over 2 or negative pi over 2, because then your tangent value will be undefined. Okay, your tangent value will be undefined. So we can do arctangent on defined values. However, we know arctangent of pi over 2 will be undefined, that's for sure. Well, so x has to be between negative pi over 2 and pi over 2. Okay, so we're going to stay with this 3 for now. Okay, we're not going to worry about secant, cosecant later on. But they follow the same pattern. You basically just follow the same pattern here. Now, so there's another set of operations that we really need to talk about is based on these composition functions, which will come very useful later when we deal with calculus. Later on, when we deal with calculus, when we deal with inverse functions a little bit more in depth. So we're really just looking at the very beginning of the inverse functions. There's a lot of other formulas and then identities of inverse functions that we're not looking at yet. But let's go ahead and take a look at this. So what about, let's look at some more advanced examples, okay? Alright. So what about, let's try, what would tangent of arc cosine of 2/3 be? So now we're venturing out into somewhere we cannot define using the unit circle, because arc cosine of 2/3, we don't know any angle of cosine that's exactly 2/3. Well, I mean, we could use a calculator to do this problem, but let's not use a calculator right now. Let's go ahead and see what exactly this means. Well, remember, what does arc cosine of 2/3 really represents? Remember, arc cosine of 2/3 represents an angle that has a cosine value of 2/3. So it really represents an angle. Okay, so what we're saying is we want to find the tangent of an angle theta that has a cosine value of 2/3. So arc cosine of 2/3 really means an angle that has a cosine value of 2/3, and then we want to find the tangent value of that angle theta. Now remember, arc cosine of 2/3 returns us an angle in first quadrant. So what we can do is we can use a graphical representation here. We can use a graphical representation in first quadrant. Now in first quadrant, so theta should be an acute angle. Okay, so what we're saying is this arc cosine of 2/3 represents an angle that has a cosine value of 2/3. Now what does cosine of theta look like in a right triangle? Well, cosine is adjacent over hypotenuse, right? Or x over r. So it means that cosine value of theta is 2 divided by 3. Okay, so based on this triangle, we can go ahead and come up with ratios. We can come up with the tangent solution for this angle theta. The only thing we are missing is this opposite side here. This opposite side, let's call it y. So we have to solve for y by using the Pythagorean theorem, x squared plus y squared equal to r squared. So x is 2, y squared we don't know, we'll find out, and r squared is 3 squared. So it's 4 plus y squared equal to 9. So y squared equal to 5, and that means y is equal to square root of 5. Okay, now because we know arc cosine of 2/3 will return us an angle in first quadrant, so this y should be positive 5, square root of 5. Okay, positive square root of 5. So that means the tangent of this guy is going to be the opposite, which is y, and then we already find out the square root of 5. So this will be square root of 5 over the adjacent. I'm sorry, is 2. So square root of 5 over 2. So this is a way to help us understand how those things work together by realizing what arc cosine really mean. Arc cosine just means an angle that has a cosine value of 2/3. Okay, so let's go and try another one like this. What about this cosine of arc sine of -3 over 5? Okay, all right. Now if it's arc sine of -3 over 5, so this well represents an angle. This well represents an angle in fourth quadrant, though. In quadrant 4. Remember what we talked about? Okay, because sine is negative. So just to make sure that we draw the pictures correctly, so I'm gonna draw. Okay, now not like that. Not like that. Yeah, something like this. Okay. So if my angle is theta here, this will look something representing in a fourth quadrant. So this is my adjacent side. So its sine value is -3 over 5. So that means its opposite should be -3. Adjacent hypotenuse should be 5. So we can find out what the adjacent is by using x squared plus y squared again equal to r squared. So Pythagorean theorem one more time. So x squared plus negative 3 quantity squared equal to 5 squared. So we have x squared plus 9 equal to 25. So subtract 9 from both sides. X squared equals 16. So x squared equal x equal to 4 in this case. Now why do I know it's x equal to 4? Because in the fourth quadrant the x coordinate is 4. So the cosine value of this angle will simply be 4/5. It's in for the first quadrant. Okay. Alright, that's very interesting. So alright, so let's go ahead and make this extend this concept a little bit further. Okay, let's go ahead and try this. What about sine of arc cosine of 3x? So we're not using numbers anymore, we're using variables. What would this be? How can we go ahead and solve this? Well, we treated the same thing as we treated before. Basically, we assume x has to be a correct number, so that the 3x will be within the domain of between -1 and 1. So if x is positive, okay, now we assume x is to be positive in this case. So we are going to return, that means our cosine of 3x will represent a theta in first quadrant, okay? Theta in quadrant 1. So this is going to be representing to us as theta in quadrant 1. So let's go ahead and draw a right triangle here, try to represent theta. So if theta is this, its cosine value is 3x over 1. So that what it tells us that the adjacent side will be represented by 3x, the hypotenuse will represent by 1. So what would the opposite side be? This opposite side, y, what would this be? Okay, so we do the same thing here. We do this adjacent, right? The sum of the leg square plus equal to hypotenuse square. So 3x quantity square plus y square equal to 1 square, right? So it's 9x squared plus y squared equal to 1. So y squared equal to, hold on, y squared equal to 1 minus 9x squared. So take square root, y equal to square root of 1 minus 9x squared. Okay, so this guy is square root 1 minus 9x squared. Let me scroll up a little bit, you can see it right here. So that means the sine value is going to be the opposite, which is y. So it's square root 1 minus 9 squared divided by 1. So which is simply square root 1 minus 9x squared. Alright, so that's sine of arc cosine of 3x. Let's try another one. What about tangent of arc cosine of x? Tangent of cosine of x. Alright, so in this case, again, we're dealing with a triangle here. We're dealing with a triangle. This x represents this angle. Arc cosine of x represents this angle theta in quadrant 1 here. So if its cosine value is x, that means the adjacent side is x, the hypotenuse must be 1. Now, so x definitely is between 1 and -1, that's for sure. And what about the y side? How would I find the y side? Well, x squared plus y squared. So let's go on this side y. So conveniently, it's just x squared plus y squared equal to 1 squared. Okay, so y squared equal to 1 minus x squared, and so y will be square root of 1 minus x. Now, of course, you can argue that if x is negative, well, even if x is negative, y can still be positive or negative depending on the situation here. But y would simply be square root of 1 minus x in this case. So tangent of this angle theta will be opposite over hypotenuse, which would be square root of 1 minus x over x. Okay, alright. So this is a very interesting situation here. We can apply this to several other ways, several other things, and this kind of technique will be useful later on in calculus when we deal with applications when we try to derive the integral, the derivatives of inverse trig functions. We'll be using this later on in calculus. Okay, so this is a short lesson today. We did several examples. If you continue to look at, I would suggest you to go on to the textbook. This is section 4.7 in our reference textbook, pre-calculus, from the publisher author Larson, and then section 4.7 they have a lot of practice problems that you can go ahead and try. So I would suggest you to go ahead and go through those problems and then practice a little bit to see how much you understand this information. Now, next section, we are going to talk about some applications of using sine and cosine functions. So we're going to be looking at that in our next lesson. So if you have any other questions and comments, please go ahead and leave it in the comment and the question sections. And I hope you join us for our next trigonometry sessions. Thank you.